Okay, part 5, lecture 8, transformation of covariant-based vectors. Okay. Now, I would like for you to pay attention on this explanation here. You see, here I have the same vector space for what I call original system. This is Ci, you see, upper indices, contravariant, and this is a basis vector, okay, covariant basis vector, okay, covariant basis vector. And also, likewise, Xi bar J, the contravariant coordinate system. This is the basis, okay, covariant basis. I call new system, okay, this is original, this is new, by convention. Then I can express, okay, this new system, the coordinates, in terms of the original system. I can see. This is just a geometric, okay, viewpoint, okay, no problem. Attention now, J and I are 1 or 2 or 3, you see. Again, I repeat, these contravariant components, okay, a coordinate, I'll say, is better. They belong to the vector space. Now, these components, contravariant components, they belong the same vector space, okay? Don't be confused with the previous videos, which will work with the vector space and dual vector space. Here, there is no word called dual, okay? It's just, I'm working only on the vector space, okay? In the original system, in the new system. Now, by definition, we already defined the covariant basis vectors in the original coordinate. Original coordinate is the blue one, okay? Is A sub I is equal partial derivative R with respect to Ci. See? And you can see here carefully, I is free, the left hand side. I is free on the right hand side. I is lower index. I here behaves, attention now, behaves as a lower index. Why? Because it stays in the denominator, okay? Always pay attention to this, okay? Now, similarly, in the transform coordinate, okay? This is AJ bar, part of the same R, you see, the same position vector, okay? With respect to Xi bar J, right? By definition. Now, I just will use the chain rule from calculus, okay? So A bar J, partial of R respect to Xj. You see the colors here, okay? They turn the explanation easier for you to see it. This is a blue one, okay? The diagonal. So you look at here and look at here. That's a chain rule. By definition, I call this term over here as Jacobian, okay? This is Jacobian. Okay? I put over here, okay? I just bring to here, this is Jacobian. Now I'm going to the inverse of this Jacobian, okay? Look how interesting. It's a very, very interesting, and I always like to emphasize. You see, here I have two free index, I and J. I is the upper indices. J is lower. Now look, on the right hand side, I is upper and J is lower. Why? Because J is in the denominator. Two free indices, the same on the left, the same on the right. You see, attention for that. This is a convention. So, the inverse, okay? AI, partial I respect to CI, okay? Again, you look the diagonal here, okay? Just a chain rule. This here, attention now, is different from this here, you see? This relates AI, in this case, okay? And this is related to AJ. Now, I just call this also Jacobian, but you can see clearly, look only this term and this term here, okay? These are, in general, two free indices. J is upper, J is upper. I is down, okay? This is AJ, okay? The basis vector here. So I related the original system and the basis vector to the new system, okay? Now, I call this relation 2 the green one and this relation 1. You see? I will just look at here. I will just substitute this term over here, right here, okay, right here, okay? I just plug 1 into 2. Then this leads to J, Ji, Jij, AI. Now, I group these two terms. See, look at here, AI, AI. You see? They are the same. This must be, this is a product of two matrices, must be the identity matrix. Okay? So J, Ji is the inverse of Jij. Okay? That's the inverse of the Jacobian. Okay, that's it.